Hello, everyone. Hi. Hello, everyone. My name is Michal Ptaszek, and I'm a software engineer at Riot Games. Today, I would like to talk about how we scale League of Legends chat to nearly 70 million players. Before we start, let me ask you a question. How many of you have ever played a multiplayer team game? It doesn't have to be a video game, any kind of multiplayer game. Yeah, so as you probably are aware, in any team game, communication is extremely important. If you could imagine a basketball game where players couldn't communicate with each other, so things like no plays could be called on the floor, no substitutions made, or no passes called for, it would be a disaster. League of Legends is also a team-based game, and communication is crucial for us as well. So today I would like to start with a short introduction to League of Legends. I would like to tell a few words how we use chat for the game, then focus on technology we use to build chat, then move forward to lessons learned, so what kind of difficulties we faced when building chat and how we solved them, and finalize with Q&A session. So let's start with what is League of Legends. So League of Legends is a team-based game from the genre of MOBA. It's a shortcut for multiplayer online battle arena. And typically in the game, you would see two teams competing with each other, two teams of 5 people, trying to control a map and achieve objectives, destroying an enemy base and also protecting their own base. Every person playing the game is controlling a single champion, a single unit, and in League of Legends we have over 100 champs right now. And everything is based in a modern fantasy world, so you would see swords and shields and also magic. So where do we have chat in all of this? So chat primarily acts as a messaging service for the game. So players are able to talk to each other using private one-to-one channels and also participate in group chat discussions. So they can hook up together and start talking with each other. The second very important thing that chat's doing is acting as a presence service. That is, it controls your friends lists, it remembers who you friended in past, and also displays their presence status. That is, whether they are online or offline, and what is their state. Are they playing the game, or are they AFK, or maybe also things like what champion they are playing, or for how long they've been playing. And finally, chat is also used pretty extensively by other services at Riot. So we expose a lot of RESTful APIs to other services on the backend. Things like Store talks to chat to verify friendships between two players. Or we have leagues that are trying to use our social graph in order to seed new players together so that they can play together more often and can compete with each other. What we observed over time is also that whenever chat is not working or it's not working as expected, player experience is getting significantly worse. And what is also important to note is that chat not only has to be up and running, but it also has to provide low and stable latency to the players. So we cannot really introduce lags in the communication. Otherwise, it wouldn't be effective. So here are a few examples of how chat looks like in the game. So on the very left side, you'd see your buddy list. So all the players you friended and their current status. And if you hover a mouse over one of the entries, you would see the detailed information, the presence. So the icon of the player, their level, their custom message they put, and also a few other things. And on the very right side, you'll see a one-to-one chat window. So everything is using chat on the backend. So to set the context for further discussions, here is the high-level overview of the scale we need to operate at. So we are very lucky to enjoy 67 million unique players playing League of Legends every month. We can see 27 million players playing daily, and during the peak hours, we observe as many as 7.5 million players logged in to the platform. That translates roughly to the numbers we see on the chat side. The number is slightly higher on the chat side because of the third-party clients connecting to our services, not using the game itself. But that translates roughly to 1 billion events that each chat server, each box, has to route every day. If you average it to the seconds, a number of operations we have to process every second during the day, it's something around 11,000 messages. So our goal was to come up with a very stable and scalable chat service, chat solution. And over time, we identified 3 components that would help us achieve it. First of all, we had to choose a protocol, the communication layer between clients and the servers. And then we had to choose the server itself, so the implementation, the routing engine. And finally, we had to choose Datastore, something that would persist all the information we would like to keep in between player logins. So let's start with the protocol. For that, we've chosen XMPP. XMPP stands for Extensible Messaging and Presence Protocol. It's basically a communication protocol based on XML, and it's primarily used for messaging, for instant messaging, for present information, for maintaining contacts lists. As it is stated in its name, it's pretty extensible. The community created a lot of extensions to the core of the protocol, which are called XAPs, XMPP Enhancements Proposals. At Riot, although we try to be as XMPP compatible as possible, it's not always available to us. Sometimes when developing new features or trying to be as performant as it's possible, we have to diverge from the core of the protocol. And we keep our own internal library of XAPs called Riot XMPP Enhancements Proposals. On top of that, XMPP is also widely adopted on the market. If you've ever used Facebook Chat or Google Talk or WhatsApp in the very early days, you used XMPP under the hood. For example, even Skype has XMPP gateway, so in theory you can connect from your Adium or Pigeon or whatever XMPP client you want to Skype servers. The second component of our service is server itself. For that, we chose Ijabird at the very beginning, and we started from there. At the very beginning, it offered us a very nice scalability and performance with pretty much no changes to the code or to the configuration. Nevertheless, we were extremely aware that one day, considering the growth and our internal requirements, we would have to get our hands dirty and start modifying it. So as a fun fact, Ijabird is written in exotic language called Erlang, you probably heard of. So a couple of words on it. So at first, Erlang is a functional language. It gives us a much faster way to build prototypes, and it also imposes a declarative style of programming. It's also built with distribution, concurrency, and scalability in mind. The language itself has language-level constructs allowing you to spawn processes, control fault tolerance, both locally in the scope of a single server, as well as globally if you run multiple Erlang VMs in a cluster, which in turn gives us more time to focus on the actual application code as opposed to fixing or coming up with solutions for scalability problems. Finally, which is super appealing to me, is an ability to perform hot code reloading. So whenever you find a bug in your code that is deployed in production, you don't have to stop the service. You just need to upload the patched file, the patched module to all your services and reload it on the fly. That way, we can eliminate downtime entirely. So when it comes to the architecture of eJabberD, or of the original eJabberD and the eJabberD we use now, we were aiming at building decoupled systems that share nothing in between, and that applies to both internal and external facing interfaces and servers. It allows us for better error isolation and traceability, and it also goes well with the scale we need to operate at. It's our aspirational state. We are not really there yet. However, we are slowly but surely progressing in that direction. More on that in the next slides. Next, because we have deployed a few hundred chat servers all around the world, and our team consists only of 3 people doing that all, we need to make sure that our service is able to self-heal. We do not have to react whenever we have a minor failure. It will auto-repair under the hood. So if you think about user sessions, so every time user connects to a server, we have his session living on the backend. Whenever that user messes up with something, starts to break the service or whatever, that actions will only affect his session context. The error will not propagate to any other users or any other services running on that server. And whenever that user session crashes for some reason, the error will not explode and will not take this whole service down. Instead, that error will be isolated to the session only and will be garbage collected. That session will be garbage collected later by our internal processes. The next thing that is quite opposite to default tolerance is the let it crash philosophy, which says that whenever we have a major failure, we do not try to slowly recover from it. Instead, we let the system or the part of the system crash, and we can easily restart it to the known stable state. That way, for instance, whenever we have a huge lag of pending queries on our database drivers, instead of waiting for them to drain over time, over a few hours, what we typically do is we restart the database driver, and all the new queries will be processed in the real time, while the queries that were queued up in the past will be rescheduled for processing later. So that the way we build the application, it is possible to reschedule that queries for later processing. So here's how our services work, or how they look like. So on the very left side, you can see 2 physical servers. And on each of these servers, we run 2 OS processes. One is eJabberD daemon, and the second one is Riak, which we use for Datastore. More on that later. So that part, the server part, is very easily scalable. We can add as many servers as we want, and we increase capacity as we add them. So they run in a clustered mode. Each eJabberD is able to talk to any other eJabberD servers in the cluster, and the same goes for Riak servers. On top of that, Riak servers use multi-data center replication to export our persistent data out of the primary cluster to the secondary Riak cluster. That allows us to run costly ETL queries on our social graph, as well as perform backups without interrupting the live service. When it comes to implementation, as I mentioned earlier, we had to focus a lot on performance and scalability and fault tolerance. And over time, little by little, we pretty much rewrote the entire HighLevel code. Today, if you asked me to estimate how much is left from the original open source implementation, I would probably say from 5 to 10%. So 90 to 95% of the code is ours and is custom to Riot requirements. So over time, we removed unwanted and unnecessary code. We optimized the protocol itself and the existing code a lot. And we wrote a lot of tests to make sure we don't break anything as we go forward. To give you an example of protocol optimizations, XMPP allows you to have asymmetrical friendships between users. So if Alice is a friend of Bob, Bob doesn't have to be a friend of Alice. For League of Legends, we only allow players to be mutual friends. So if Alice is a friend of Bob, Bob is automatically a friend of Alice. So XMPP, in order to establish a fully functional friendship, required us to send something about like 16 messages back and forth between clients and servers. And that was hitting our data stores pretty bad. What we've done instead, we changed the protocol a bit, and we made it that way so whenever Alice sends an invite to Bob and Bob replies, the friendship is already established. We don't have to shake hands once more. The next thing we had to do was to profile the entire code and look for obvious bottlenecks. Things that do not scale, that share state across multiple processes or multiple nodes, and try to make it so that it can scale linearly on single server as well as in the clustered environment. So as an example, again, here, MUC is a multi-user chat, is an abbreviation for multi-user chat. So every chat server can handle hundreds of thousands of user connections. And for every user connection, we have a session process. Every time a user wanted to send a message or post his presence update to one of the rooms he was a member of, that event had to go through a single process called MUC router. That MUC router was basically a messenger that was relaying all the messages to particular group chats. On a multi-core system, that was a disaster. You can think of it like of a critical section that spreads all over the few hundred lines of code in your C++ application. So it was a clear bottleneck to us, and what we've done was we parallelized the routing, and the whole routing concept, the whole lookup for a group chat room happens in the context of user session, so that now we are able to use all available cores at any time we want. The other kind of optimization we implemented for chat was every HighLevel server contains a copy of so-called session table. So session table, you can think of it as a translation table between Jabber identifiers and session handlers, that's session processes. So whenever you want to send a message to someone, you know his JID, Jabber identifier, and you look up where is his session in the cluster. So in the original HighLevel, whenever a user was posting a presence update, say Bob finished his game and he went back to the game lobby, so he posted an update. HighLevel was writing down that presence update to the session table. So effectively, even though his session handler didn't change, there was a write to that table. By first checking if the session exists and checking that the presence priority is correct and stuff like that, we were able to reduce the number of distributed writes to that table by, I think, 96%. which was a huge win for us. We were able to log in more users faster, and we were able to also allow users to change their presence updates much more frequently. And finally, we had to take a closer look at the Erlang VM itself and the OTP libraries it comes with. We were aware that by changing the VM and the standard libraries, we are sacrificing the generic nature of Erlang OTP in favor of better performance or better scalability. So on the application side level, on the libraries level, we tried to get more visibility into what's going on whenever we deploy the new code to production, whenever we hot code reload. In the past, the original Erlang OTP framework, whenever you upload release upgrade package to it, it will only output 2 messages. First one will be, okay, I'm beginning to migrate your system from version A to version B. And the second message would be, it was successful or it failed. Whenever we perform a larger upgrade and we need to change, say, 100 files, getting a message saying it failed, it doesn't really help us. So we added a lot of logging, a lot of visibility points into that process so that now we can keep track of progress on every single file level. And we can also have an ability to reload the code on multiple servers at once in a transactional context. The other thing we had to do for optimizing our servers was to build in debug functionality into the VM itself. So to keep the memory footprint low for every session handler that lives on the server side, we had to have an ability to inspect what that process is allocating and what it's wasting memory on. So for the Erlang VM, we added a functionality to inspect the heaps of the processes so that you can point to a session handler process and ask what kind of terms that process allocated has on its heap and how many machine words each term consumes. That way, we have a clear picture of memory utilization and also what are the parts of the session state we should take a closer look at. Finally, the Datastore for chat. With the number of players Riot enjoys, we knew that scalability would be an issue from the start. We opted in for NoSQL, which, as you know, sacrifices the ACID benefits of traditional SQL storages. Initially, we started with MySQL. However, over time, we were stumbling upon multiple performance issues, stability issues, and flexibility issues when we were not able to manipulate MySQL schema fast enough to keep up with the changes we made in the code. So we chose Riak. Riak is a distributed, fault-tolerant key value storage. It's truly masterless. So whenever we have an issue in the live service, when one of our servers dies, there is no single point of failure. We can afford losing 2 of the servers on production and still be able to operate without losing any data, without losing any functionality. Riak implements availability and partition tolerance in the CAP theorem, and it's sacrificing strong consistency. So for that, we had to spend a lot of time on the client side, on the client from the Riak perspective, on the server side, the chat servers. And we implemented HighLevel level CRDT library. CRDT stands for commutative replicated data types. So that library takes care of all the write conflicts that happen in Riak and tries to converge the objects to the stable, predictable state. Over time, it proved to be a huge success. It allowed us to scale linearly, and it also gave us a flexibility in terms of changing the object layouts and playing around with features. Nevertheless, it required a huge paradigm shift. It required a lot of work on our end to change our way of thinking, and also how we test our services and how we build tools around it. Let's move to lessons learned. So first of all, we realized that the key to success is to understand what our system is actually doing. So monitoring is key to see whether your system is in a healthy state, whether it's about to crash, or whether it's being attacked by some malicious users. So we've built over 500 real-time counters, rates, histograms into EJBRD code. They are all collected every minute and posted to either Zabbix or Graphite that we use for monitoring. For every counter and every metric we collect, we have thresholds that define regular or normal conditions, as well as abnormal conditions. So whenever when any of the counter values goes way off the limits, NOC is automatically notified about that fact, and we can react pretty fast, even long before the players can realize there is a problem on the service. So a fun story about it is a few months back in time, we released a very buggy client update. The client code itself was pretty much broadcasting its own presence every time it was receiving a presence update from someone else. So you can imagine an infinite loop of presence updates flying around the network. So we were wondering why our chat servers are so hammered with the load. And by briefly looking at the graphs, at Graphite, we were immediately able to realize, okay, that additional traffic is actually presence updates. And they started to show up exactly at the time when we released the new client update. And after patching the client, which was relatively easy, we were almost immediately able to verify that the fix worked and the rate of presence updates went back to the normal level. And another thing we found very useful when building new features is to have an ability to turn them on and off on the fly without having to restart the service itself. So whenever we come up with something new, we're typically surrounded with the on-off toggles. And that way, if that feature causes any problems, we can safely disable it. Yet another thing we've built for our chat servers is an ability to perform partial deployments. That is, we can get a new code and enable it only for selected users. For example, we can provide a list of user accounts that would have that particular feature enabled, or we can express that only 1% of our player population will see that feature in live. That allows us to test potentially dangerous features at the lower scale, and if they behave okay, we can then turn it on for all the players. Another thing, which I mentioned earlier, is ability to code reload on the fly. So a few times in the past, we were unfortunate to release code that wasn't really well tested on the third-party clients. So it was working fine with the official client. However, Adium or Psy or Pigeon were sending a different type of events to the chat servers than our client, and that was causing problems. So we had either an option to patch the buggy code, perform the server restart, and run with the fixed code. Or what we could do with Erlang and with the way we built our release upgrade system was we were able to upload our changed modules to the servers and apply them without having to restart the whole chat. That, of course, translates to lower downtime for the players. The next thing is logging. It's pretty obvious, but it's really important as well to get it right. So for that, we not only try to log all the abnormal conditions like errors and warnings, but also try to make sure we keep track of a healthy state of the server. So servers report healthy state over time, and that way, by briefly looking at the logs, we can immediately identify, okay, that server is okay, because it's logging users, it's accepting new connections, it's modifying friends lists, for example. On top of that, we build a functionality to enable debug modes for selected user sessions. So if, for example, you have a suspicious user, or if you have an experimental user, a QA tester who is testing his things on production servers, we can turn on debug mode for that particular session, and that way, even though we have 100,000 players connected to that particular server, only that session is emitting megabytes of logs, including all the XMPP traffic, all the internal events, and all the metrics related to that particular user. That way, we are able that if you combine that with the feature toggles and partial deployments, we can actually deploy the feature to production servers and let it be tested only by few people. That will emit tons of logs for us so that we can take it back to our development machines and optimize it or change if it is buggy. Then always load test your code. So by that we mean that we have an automatic verification system of our latest changes. Every time we change something, that very night we have a Jenkins job that picks up the code, builds an artifact, deploys it to one of our load test environments, and runs a battery of load tests against it. It's not only spinning up clients that are hitting the chat servers, it's also monitoring the health of the server. So it's pulling the metrics from it, it's analyzing them, it's creating that beautiful Confluence page with tables and all the counters, metrics, and everything. And also in the morning, we find an email summary in our mailbox saying that this was successful or it failed. We also have an ability to compare our changes to the previous builds so that we can keep track of the impact of our code changes, whether it was a disaster or whether we improved memory consumption by 50%. And lastly, things will always fail. I mean, we have no control over everything around us. You can think about it that in a way that even though in theory we can come up with a bugless code on the server side, there will be external factors such as ISPs. What happens if one of the main routers at the ISP side dies and we lose 100,000 players at the same time? Or if the hardware melts, or if we have problems in the network. So you have to be prepared for that situations, and you have to make sure that your service is able to handle losing half of your logged-in players at once, or is able to handle losing 5 out of 20 chat servers without degrading performance. Also, no code is bugless. So even if we have a code that works in most of the cases, say a bug happens once every 1 billion times, at our scale, it will always happen on each chat servers once a day. So even unlikely events will always happen over time. So where are we now? Chat is doing great. We can enjoy over 99% of quality uptime. Our aspirational state is to reach the mythical 9 nines of availability. We are slowly going there. When it comes to scale and performance, we have a few hundred servers, physical servers deployed in production. And as I said, every chat server deals with at least 1 billion events a day. And that happens with relatively low resource utilization. It's something in between 20 to 30% of available CPU and RAM. And chat is evolving. It's not a complete product. What we are doing right now is we are migrating data off MySQL worldwide. We are still in the transitional state. The second thing we would like to do is to make League of Legends chat available outside of the client, outside of the game, so that players can enjoy their friendships without having to log into the game itself. And finally, on the backend side, we are exploring possibilities around reusing our social graphs to make the whole experience better. So analyze the connections between players and understand how they impact their enjoyment in the game itself. That's it. Thank you for listening, and I would love to hear some questions. Sure. So the question was, can I describe CRDTs in more details? So the concept we use is, instead of storing object values, say you have Alice and her friends lists, like it has Bob, Charlie, and Eve, we don't store, and every time we update that list, like by appending new item to that list, adding new friend, we don't store the list itself, the new value. Instead, we maintain an operational log to that object, which will say add Bob. So whenever two updates happen in the same time to that particular object, we would end up with two entries appended to the object log. We would have add player 1 and add player 2. So next time we read the object, we will detect a conflict, a write conflict to that object. Then we would take that two objects and merge the logs, the operation logs, and apply them in any order, because the order doesn't matter. That way, we end up with a consistent state of the friend list. So basically, the concept is you do not update the value that is stored in the data store in place. Instead, you build a long log of operations to that object, and you apply that operations whenever you read the object itself. All right.
The in-game messaging, is that similar or dissimilar to the chat system?
So currently, okay, so the question was whether the in-game messaging is similar to out-of-game chat. So currently, the in-game chat is using game servers to route the messages between players. However, I think the plans are to migrate it off the game servers to the chat servers themselves, so that we can use all the goodies we have today for out-of-game chat for the in-game chat as well.
Well, even the gameplay messaging around like present, like location, movement, stuff like that.
Oh, so that's totally different thing. So that's totally out of scope of chat, and that is dealt with. That's dealing with the game server itself. Anyone else? It's pretty light here. Right. Thank you all.